Hey everyone, sorry about the delay from my last video. I've been crazy busy. I put up a game on Steam for coming soon. It's going to be in Steam Next Fest in October, so I know that's a long ways away, but this is for A Beaver's Tale. If you like cozy adventure games, whatever, if that's your jam, with nice background music and some cool leaf particles and things like that flying through the air, then go ahead and give it a wish list. But today I want to talk about procedural generation, and we're going to do some of that in Godot. I want to play this little clip from a game called Tiny Glade. I'm going to put their link down below, but I saw them in Steam Next Fest and I played the demo for a little while, and I was just completely amazed at the procedural generation system for how the bricks work and the different things in the game. So let's just play a little bit of this and watch it. So even just watching them make the walls, there's so much other stuff in this video and how their game works. It's really cool. But it's obviously procedurally generated. We can see that it's following this curve, and it seems to reseed the random generation for the mesh that it's using, kind of at increments. So it looks very visually appealing. And of course, with that brick sound effect, it is a really interactive experience, and it's very fun to play with. Okay, so let's jump into Godot. I'm in Godot 4.3 here, and let's take a look at a little version I mocked up of this because I saw this idea and I was just like, I have to try something to try to replicate this because it's so cool. But what I have here is I have this little scene, and it has a bunch of these brick objects. So let's just jump to Blender for a second. I'll show you what the bricks are made out of, how they work. It's just a really simple rectangular prism with a bevel modifier on it. I have wireframe on here so you can see exactly what this thing is made out of. But of course, if I apply the modifier, then you can actually see the vertices. My original idea was that we could take the bricks in the wall and just kind of stretch them as the size changes. But that really doesn't look good, and as the size changes, you could have defects in the mesh. Jumping back to Blender for a second, if we take this and stretch it this way or stretch it this way, you can see you get a good bit of deformation of that curve kind of at those edges. So the next thing I thought to do is we should probably take these vertices and pull them out, and these vertices and pull them out, right? To be able to resize the brick dynamically, preserving the shape of the curve, the bevel here. Okay, so that's the basic idea. And one thing I will note, we are using forward plus here on the Godot side, but there is something really interesting you can do with this. If you look in the bottom right corner here, you'll actually see that there's only a single draw call happening. So Godot 4 does batching very intelligently. We don't need to use a multi-mesh instance. We can actually just use some node 3Ds with a bunch of mesh instance 3Ds. So when you initialize it, basically it's reseeding. Let's go into the side view maybe, and maybe this way. Yeah, it's basically reseeding that random size that's applied to each brick, but it's also clearing out this whole scene tree and then repopulating them with the bricks. I don't think this is the absolute most efficient way to do it, but it does work. And then you can change the length. Say if you change that to 2, it'll resize it to match that, right? And then you could change the number of rows to 3 or whatever. I think in Tiny Glade on the top row, they actually kind of skip some bricks, right? So they deliberately, maybe every third or fourth brick they're leaving out to kind of give it that castle brick edge kind of look. You'll notice that I have a lot of export variables on my script here. Basically what you can do is you can make your code a tool script to prototype and iterate really quickly. And that way in the designer, you can just click those setters. I'll show you this. I do this pattern all the time, but I have this little init Boolean up here. And if you look at the export setter, it says basically if the value is true, then we're going to run this function, but I never actually set the value. So I don't need to keep track of this as a state or anything. Basically, it just acts like a button, right? It's a button I can click. And then all these different parameters I can mess with. Change this to 0.1. We'll see that we'll probably get a lot more uniformity. So I'll show you how this is implemented in a second. Maybe let's increase the length to 4 and change this to -0.2. I think those were the numbers that I kind of liked the look of at the beginning. But let's take a deeper dive into the code. It's really not that complicated. We're just using the multi-brick init function. And I'll kind of walk through it, explain what it does. Basically, it's going to look for all the child nodes in the multi-brick node 3D here. And the first thing it does is just clear out all the children. We're going to find the maximum brick size. We're going to use this later to try to find the end condition. And the basic idea is we've got a for loop for the number of rows, like the height of the wall, and then another interior for loop for each of the columns. And really the algorithm itself is probably easier to talk about. It's quite simple. You know, we start on the bottom and we just generate a brick with a random size, and that random size is going to deviate from the base mesh, right? So keep in mind the base mesh has certain dimensions. In this case, the base mesh has 0.3 on the y-axis, which means it'll actually have 0.3 on the x-axis with the way I have the rotation set up here. But basically, it's going to have that 0.3 meters plus or minus some variation, and I have the minus set at minus 0.2, so it could be as narrow as 0.1 meters, so some of these are probably 0.1, but it could be as big as 0.5, right? 0.3 plus, or 0.6, 0.3 plus 0.3. And the algorithm, all it says is we're going to iterate along the bottom, and we're going to generate a random brick size, place it, and then go to the next one. Place it, go to the next one, place it, go to the next one. And then obviously we have to have some termination condition on this side. So that's exactly what we do here. There's some stuff up front that we're just resetting some variables. We create a new row. We drop this as a node 3D into our multi-brick node. And then for each column, all we're doing is we're using a random number generator. So I instantiated this up here. And we're calling rand frange on that brick min and brick max, right? So we're going to get a range from anything from -2 to 0.5. So this brick size is going to have the base size plus the random size change. All right, so this is actually our end condition here. If the total length on any row goes beyond that desired length, so in this case, our desired length is 4 meters, right? So that's why it cuts off so nicely, right? If it goes beyond that, then we do a little resize. We set our brick size to be the desired length minus the total length. So the total length is going to be something less than the desired length. So we're just making sure that the last brick fills the space to give you the total length. The brick center is a little bit tricky, and I'll try to explain the core of what's going on here. Basically, the magic here is really about using instance shaders. So all of these, the reason we can batch them into a single draw call is because they all use the exact same material, right? We know they're using the same mesh, so that's good, right? We're obviously loading them up with the same mesh, but then we want them to use the same material. If you use different materials, then you're doing a material switch, which is going to be a different draw call. All we're going to do is we're going to take whatever the vertex points are, and this, remember, this is in local coordinate space by default in Godot, and then we add that brick size minus 0.3. So if I set a brick size of 0.5, I'm going to subtract the base size, which is 0.3. In this case, if we look, this dimension is 0.3. So this is like the delta. This is like the change in brick size. Think of it like that. And then we divide it by 2 because we're actually going to be stretching both sides. We're going to be taking this side and pulling that out, taking this side and pulling that out because we're multiplying by the sine function. So we're not scaling the coordinates. We're actually grabbing all of the vertices that are, say, to the right of the XZ plane and pulling them and actually shifting them. So that's why we have a plus sign here. We're doing a vertex offset is probably a good name for it. So the shader itself is super, super simple. And if we look at any one of these instances, we can actually go in here, right? Let me try to get my cursor. There we go. We go in here and we see even the extents of the box. It will always show you that little orange highlight in Godot. It will show you the extents of the original brick and how it's been scaled since then. If you come in here and you go to instance shader parameters, you're going to see this brick size uniform, and that gets set from our code, which initializes it, right? So that all comes back to here. We have this brick size that is going to be the base brick plus that random change, and then we just feed that right into the instance shader uniform, right? So we're setting that externally, and then all of those objects get that instance shader uniform. So all that to say, basically, we can do this all in one draw call, so it's very efficient. Of course, your triangle count will get up there. And maybe in this case, I didn't need to do a double bevel. Maybe I could have done even just a single bevel. So I've got a lot of geometry here, and I probably don't need that. I'm going to come back to the brick center in a minute. Then we set the RGB. So it's just a random with some colors I liked. And then I'm just using a transform. Not really any reason. We could have just used position, I think would have been fine, but I'm just very used to using transform 3Ds now. So we're going to place the Y coordinate on the row it's on. So row 0, row 1, row 2, row 3, right? So we're just bumping that up by the brick size. It's pretty intuitive. And then that variable brick center, which we're going to come back to. After that position is set, we're actually going to set the last brick center, last brick size for the next iteration. So the next brick that picks it up will know where was the previous, right? So if you're this one, you need to know what was the previous center point for this brick and what was the actual brick size. Forget the orange box, which shows you that default brick size. What was the actual brick size that was used? And then what we grab is we grab this center position plus half of its size. And then we're going to add that to half of the next size. So if we jump back up here, it's going to be this brick size divided by 2, right? So it's going to be that current brick size, which is half of this, right? Plus the last brick center. So in this case, it's going to be this guy's center plus the last brick's size divided by 2. Which would be, it would just be half of this. I'm a little too close right now, but half of this distance here. So a really simple algorithm. The termination condition, like I said, it just chops it off so that the last brick fits that perfectly. And then if we queue last, then we actually break from the loop. Now the column loop is not set up super intelligently. You could use a while loop, that might be better. But right now I just have a maximum number of 100 bricks that it can generate in any direction. Okay, so the other thing I wanted was an actual test bed to work on this code and see it actually working. So I won't go through all of this, but a few things that I find super, super useful. One is just a free look cam. One weird thing about this add-on is that it will try to install in your project root. You probably don't want that. So let's see if I can find it. Yeah, it's still here. When you go to download this free look cam, it's a great little script, but yeah, it will try to install right in your root folder. So you can change the folder of an add-on. It's pretty simple. I use my own protobody add-on along with Kenny textures just to slap down this static body surface for the floor. And yeah, that's about it. Basically what I knew I needed in this case, I knew I was going to need to project my mouse onto this, static body to replicate what Tiny Glade was doing. Obviously they're drawing, right? So I wanted to simplify this. We have this cursor that shows up when you move the mouse. When you drag, I'm snapping on the length of the distance and I'm snapping on the angle. So this seems like a really simple thing, but I actually do want to go through this because basic knowledge of vectors and trigonometry basically is how you can solve this. But I think some people tend to really overthink solutions like this. So that's kind of the basic idea. And obviously what we're going to do is you're going to pick a spot, you're going to start drawing. And when you start drawing at each one of these snapped intervals, I want to reseed that brick wall so that random pattern changes. Let's first take a look at just what this code does. All I'm doing, this is bucketed code that I use on a bunch of projects, but I have the input. You're going to grab input event mouse motion and input event mouse button. I usually separate these and try to break it up into as many pieces as I can. Basically, I'm going to do the hit calculation, the actual raycast, every single time the mouse moves. In my experience, it doesn't seem too crazy. I actually don't need this other layer here, but you can just do it on layer 1. So we're going to do that raycast. I'm going to store the hit in a global variable. So we're just storing hit position in this global class variable, whatever you want to call it. Right, so every time the mouse moves, we do that. And then I break it up into a hover action and a click action. And the click action lets me capture precisely when we're starting and when we're finishing. So it just makes the code really clean. And what I'm going to do now is I'm actually going to bring this back. So this is the wall generation code, and we'll take a look at what this does. But yeah, so now as we drag, we're actually getting this reseed each time. It looks a little slow, but that's actually deliberate. I'm gating this, how often this happens. It's not happening every single time the mouse moves, and I'll show you a little trick for that. But I thought this looked pretty good, honestly. Like, it's the basic effect that they have in Tiny Glade. Now they've got, beautiful art going into it, but I think there's a lot that you could build on and make some really interesting stuff with this idea. Let me go over the angle stuff just for a second. So when we're hovering, so the mouse is moving, we've already got the capture start, and I'll talk about this debounce in a second. It's a pattern you can use in Godot a whole bunch to kind of gate how often something happens. If you don't want it to be happening every single scan or every single input event firing, you're going to overload your CPU. You can gate that, right? In this case, I have the hit position and then the capture start position. So the capture start position is when I first drag the mouse. So this vector is basically going to be, it's exactly going to be the beginning of the wall. In this case, if the wall points here, if you look where the blue starts, the blue started here and it ended here. This is the capture start position, and this is the, the position that we end up dragging to. So all we're doing is we're basically creating a vector here. And then we get the length of that vector, and I'm snapping it to 0.25 increments. The next thing we do is we look at the XZ space of this vector, right? So everything is perfectly flat here. You could get fancier with this. And in my recent game, A Beaver's Tale, I actually did get pretty crazy with the transforms in the building system. Probably going to do another video on that later. But for now, we can just look at the X and Z components and just treat it like a 2D vector. So I basically grabbed X and Z, treat it like a 2D vector, and then we're going to get the angle, right? So we're going to snap the angle. We're going to use tan2, which is basically, arctan y over x, right? Pretty much. And we're going to put in minus y of the y, I'm using y in quotations here, component, and the x component, right? So we grab that angle. And what I would just say about this is if you use cosine or sine, you're going to have issues with, you're probably only going to get 180 degrees of the plane, and then the other 180 degrees aren't going to work. But anyways, I think you should just use the inverse tan function. That will work better for capturing your angle through the whole 360 degrees. The next chunk of the code basically checks to see, is the capture length new compared to the last time we had an input event, or is the capture angle new? So this will only snap to those 15 degrees. So we're not doing anything crazy. And then we'll talk about this code in a sec, how we're actually generating the wall. It's really simple. But we're actually going to debounce this. So we create an await, get tree, create timer, 0.2 seconds. And what this is really doing, .timeout is a signal that's emitted by the create timer. And await will actually inform this function to hold up and say, wait until we actually get the timeout signal from the create timer. It doesn't hold up the whole show. It's not going to hang your game. What it's actually doing is the event that this frame fired on, or that this code fired on, will wait. But it will actually get more events. We'll get more events immediately after, even if this guy's waiting. That's kind of the nature of await. So when you do this, we need basically a condition to block any further, hovering or mouse motions from triggering that wall updating. Otherwise, you're just going to slam your CPU. Mostly with queue freeing everything in the tree and then repopulating it. The graphics side of this is very, very minimal. It's really, really not a big deal on the GPU. We have the current brick wall, and maybe I skipped that a little bit, but when you click mouse down, you just instantiate that packed scene, right? You have a const brick, and I haven't showed this, but I think some of you might know this, but basically you can drag and hold control. That's like the most useful thing in Godot. I use it all the time, even for grabbing stuff like this. But you can control grab your packed scene, bring it into your node here, and then you can just use it, right? So we instantiate it. We add it to this walls section. So sorry, I'm in the wrong place, but if we look at walls, it's going to add it here. And then we set the current brick wall to that new brick wall. And we actually hide it right away because when you first click down, I'll show you this. When you first click down, we haven't actually dragged to any length. The length is 0. So you actually need some initial length before you start generating that, that wall. All right, so that's the basic gist of the code. We're using the desired length. We're setting the position and we're setting the angle. right? Based on that start position, that stuff is fairly simple. And then we call multi-brick init each time. What I will say about this, I mentioned earlier, this is not the most efficient way. It's not the most efficient, but you have to get very clever with your resizing algorithm. So your resizing algorithm would have to iterate through all of these nodes and check to see, if the size is decreasing, then some of those nodes need to be removed. It's actually always going to be the ones on the end. And then if you're increasing, then you need to add some. And then the question is, do you actually want to reseed the animation each time? So there's better ways to do this. And I'm actually a little bit tempted to do this in C++ to see if the interface would be any faster on GD extension, because I know we're doing a lot of node assignment as well as node freeing. So having that go over the GD script interface could be slowing things down a touch maybe. But yeah, that's basically it for the video. Hope you enjoyed this. I hope you got something out of this. Like and subscribe if you like this kind of stuff, and let me know what you think in the comments. See you later.